Hello friends, in this video I will discuss the synthesis of nanomaterials, and there are two approaches, top down and bottom up. There are two approaches, top down and bottom up approach for the synthesis of nanomaterials and nanostructures. In top down approach, we start from the bulk material and then reduce the size using the mechanical or chemical methods. Whereas in case of the bottom to top approach, we start from the atom by atom or molecule by molecule, and then we will make the cluster and then nanoparticles using by chemical or biological procedures. And here in this image we can see we have started the top down, means when we have started from the bulk or the bigger particles, and if we make the smaller and smaller particles, and finally we get some nanoparticles. Whereas in bottom to top approach, we start from the atoms or molecules and then we make the clusters and finally we get the nanoparticles or nanostructures. So this is the top down and bottom up techniques. And in top down approach, we use usually physical methods like milling method or some electron beam lithography or normal photolithography. These are the techniques. Whereas for the bottom to top techniques we use the chemical methods like co-precipitation, sol gel, and hydrothermal methods, and also for the biological methods are used for bottom to top technique. Top to down approaches are like we can make by ball milling, where the bigger particles are made to smaller particles using the high energy ball milling method. Also, there is one laser ablation method where laser is used for making the metal nanoparticle. And third one is lithography. And lithography is the process of the transferring a pattern into the reactive polymer film or some substrate. In case of ball milling, it is a method of production of nanomaterials by milling the bigger particle or big micrometer size particles in some nanometer size particles, and there are some zirconium or some steel balls in these vessels, and then it is grounded for long time, and then we get the fine powders. But this method have some limitations. This is the machine. In these jars have the powders with some small balls inside this, and they get milling processes there inside these balls, these jars, and this is the lid, and it can rotate also. And finally, after many hours, we can get different sizes of particles. Suppose after 3 hours we have some micrometers, few micrometers, and after 20 hours or maybe more, then we can get some particles in nanometer range. We can see the with increase in time we are getting the smaller particles. So this is about the ball milling process, but this procedure is very time consuming, and there are always chances of some impurities in the powders. Laser ablation method is another method to get the nanoparticles. Suppose we want to get the nanoparticles of silver or copper or any other metal, then we have to have a laser source, and if we put throw the laser on this metal piece, then we can get the silver or copper nanoparticles, and it may be yellow color or green color depending on the size of the nanoparticles. So this is the laser ablation method for making of nanoparticles. So lithography is the process of transferring a pattern on the substrate using some photoresist or polymer film, and several techniques are used to make this lithography, and some radiations used like photons, X-rays, or electrons for developing the structure. And the lithography techniques have been used in the field of electronics and electronics, and of optics and photonics also. And it is photolithography is the most widely used technique in the case of microelectronics fabrication and production of integrated circuits. And in case of the photolithography, a mask is used to make the pattern, and optical technique into the polymers or photoresist to get the structure on the substrate. And photoresist material is applied as a thin coating over the silicon wafer substrate, and then it is exposed to the radiation or UV light. And in this case, UV light is used to get the desired pattern, and the photoresist in the case of the exposed area, the photoresist breaks down, and then we use the developer or the solvent to remove the photoresist, and finally we get the desired structure which was used by using the mask on the substrate. Here we can see in this image that if we have a silicon substrate or silicon wafer, and on this we want to make some channels for some transistor or some integrated circuit device, and we have a mask, and first we have to put a photoresist layer on top of this silicon oxide, and then the mask, and then using the UV beam we will get this photoresist gets soft if it is positive. There are positive photoresist and negative photoresist. In case of the positive photoresist, when UV light falls on this photoresist, we can easily dissolve it or it gets soft. Whereas in case of the negative photoresist, if the UV light or radiation falls on it, then it becomes harder and it will be stay here, and the other part we can dissolve it. So then finally we can etch the silica layer to get this kind of device to make the some microelectronic circuits. And this is how we can put on the wafer some photoresist, and this photoresist it is a mask, and if we expose it with UV light, and finally this is developed in a solvent, and then we get the final structure on the wafer. So this was the photolithography techniques which is mostly used in the semiconductor industry. Now we will see some bottom-up techniques, and there may be some liquid phase synthesis, gas phase synthesis, and vapor phase synthesis, and we will discuss some of the examples for these. And for the liquid phase synthesis, there are several methods like co-precipitation, sol gel, microemulsion, hydrothermal, and microwave synthesis also. But we will discuss just co-precipitation and sol gel processing here. These are easy method to prepare the nano powders or nanoparticles. Suppose here we have in co-precipitation method, we take two aqueous solutions and we mix it with NaOH, and finally we get the two components AX, BY in solid form. Here, like suppose we can see the co-precipitation method for the synthesis of copper tin hydroxide nanoparticle. So we take the copper chloride solution, tin chloride solution, and then we add the NaOH solution in this, and now it gets precipitated here, and the solvent is filtered, and after filtering it is dried at 80 degree, and finally we have as prepared copper tin hydroxide, and this is heated at 400 degrees centigrade for 3 hours, or it is calcined. Calcination means it is a process to complete the reaction in the unreacted powders to get the final form of this material. And now we have the very fine powders, and using SEM we can see the size of the nano powders. And this is just the block diagram. We have the cation solution and anion solution, and we have the precipitation here, and we have to filter it, and then we have the as prepared powders, and this powder can be calcined to complete the reaction and to remove the other unwanted organics. And finally, after grinding, we have the very fine powders or nano powders made by co-precipitation method. Similarly, soil gel processing is also very important process for making or for synthesizing the nano powders, and it is a low temperature process and a low cost process. And in here also we take the solution and make the powders. This sol is the full short form of the solution, and then this solution is after heating, it makes a viscous gel which is known as the this gel integrated network, which is known as the gelation process, and it is gel. Then it is known as sol gel process. And in this case, the initial material were used as metal alkoxides or metal chlorides are used in the solution form, and then this solution is again it is heated, and then the water is evaporated, and finally we got the viscous gel, and it is, if we heat again, then it becomes in very fine powders, and after the heat treatment or the calcination process, we get the finer further material in nano form, nano powder form. This is diagram shows the sol gel method, where the solutions of precursors are here, different chlorides or alkoxide. These are the solutions are here, and after that there are some they heating, they get some gelation or a network of the elements in this, and finally we get after drying this, we can directly dry this and we get the gel in very dense form. It is known as zero gel, and this if we again grind and heat it, then we have the fine powders of this material. Similarly, if we have this gel, and if we sintered it and make some like disc or any another shape, and then we have the dense ceramic using this powder. So we can also make the ceramic or denser material using this gel method, sol gel method, and it can be also used. This sol or this solution can be used for making the thin film or the layer on a substrate using dip coating or some spin coating, and then we get a dense thin film. And also we can also get some kind of fibers using these solutions. And so these are the different products we can make from this sol gel method. Either we can make the thin films or layers, we can make very thin very fine powders, and also we can make some dense ceramics using this sol gel method. So it is a low temperature method, and it results in very fine nano powders. Suppose this is the method how we can prepare the titanium dioxide nanoparticles by sol gel processing. We can take the alkoxides of titanium salt plus H2O or water is used, and then we have a solution, and if we heat this solution, then water will go out minus H2O, then it will be gel, and this gel again we heat it up, so we will get very viscous gel, and it is also known as the zero gel. And if we heat it more than 400 degree, and then we have titanium oxide, and it is very porous powder, and we can see also from the SEM or TM images, like we have the very fine particles of few nanometers using this method, sol gel method. Now we see the second method, that is gas phase synthesis. And in gas phase synthesis, the cooling of the saturated gas or vapor in specific conditions, and we get the nucleation and growth of the nanoparticles. Using these gases, it agglomerate, and finally we get the nanoparticles here. Suppose this is an example of preparation of titanium dioxide particles. We take the titanium chloride gas here, and then oxygen gas, gas B, and then inside this chamber there is some reaction, and after if we move in another direction, so these particles will settle down, and finally we get the titanium oxide particles here, and the unwanted gases or the chlorine or these other gases will be go out by this other side. So this is how we can prepare the uh, uh, gas phase synthesis. And now the third one is the vapor phase synthesis, and in this case we have two kind of vapor phase synthesis are there. One is physical vapor deposition, PVD, and another one we will discuss later, that is CVD, that is chemical vapor deposition. And it is a process of transferring the growth species from a source or the target and depositing it on the substrate in form of the thin film. And in PVD method, either these atoms can be either by evaporation or by sputtering. We can get these atoms from the target. And in evaporation method, it is a low pressure method, like we need some vacuum 10 to the power minus 3 to or more, and then the material is deposited on the substrate in vacuum, but the film quality is poor in case of the evaporation method. And then sputtering method or pulse laser beam method are used for getting very high quality thin films. In physical vapor deposition, the target or the source is heated and it is evaporated, and then we can deposit it on certain substrates. And this is a chamber which is at vacuum, and it can be used for coating of various metals or alloys in case of semiconductors. So this physical vapor deposition we can use for where we don't need very high quality films. Sputtering is used when high energy particles they struck the target, and then we get the atoms from the target, and then we can deposit the films. And most of the metallic film like aluminum or titanium or some alloy films can be deposited using the sputtering. You can see that high energy particles are coming, and then they eject the atoms from the target, and it can be deposited on the substrate. And ions are generated and directed at a high energy ions. Suppose argon ions are there, and this is the sputtering target, and it will strike, and then the atoms of this target will deposited on the substrate, and these ejected atoms are transported to the substrate, and the atoms of these will be deposited on the substrate. And this is the actual system. And sometimes it is there is some sputtering gas, suppose nitrogen or some inert gas is used in this chamber. One another method is laser ablation, and it is mostly used for the carbon nanotubes from graphite. And in laser ablation method, pulse laser is used to vaporize the target in a high temperature reactor. A reactor is there, means a tube is suppose quartz tube is there, and this is inside a furnace, and some laser, suppose here is ND YAG laser is there, and from the target the carbon or some carbon nanotube, they can be deposited on, suppose some substrate is there like copper or any other metal, we can get the graphite film here. And the laser ablation yields around 75%, means good quality of carbon nanotubes can be grown using this. And it is little bit expensive than the other CVD systems, because here we need the laser also, and also this chamber is there, so it needs some sophisticated instruments. And now chemical vapor deposition. In this high quality films are deposited, and this is used in semiconductor industry to produce the thin films or layers. CVD is a process where gases precursor react to form a solid coating on a heated substrate. So reactant gases are they are moving inside the chamber, and this chamber is at high temperature where substrate is here, and on this substrate the reactant gases, suppose some chloride is there, and plus hydrogen gas is also reactant gas is there. So this chloride MCl2 plus H2 will react, and this this metal will be deposited on this substrate, and the HCl gas will be, waste gas will be out of from this site. So this is the CVD process, the mechanism of the CVD process, and it is used for deposition of many semiconductors on silicon or another substrates. One another method is atomic layer deposition. This is also a very good method for semiconductor industry, where we need to deposit the films on different geometries. In case of like cylinder or some on trenches of some silicon substrate. So it is advantageous, and it have very good control on the thickness, and we can go even the mono layers in case of the atomic layer deposition. And in this case we have to use the inert gas for purging, and the precursors are also gases, and we can understand using this image that starting surface is there. Suppose this is a substrate, and precursor A have some gas inside this chamber, and the atoms will be deposited on this, and again there will be some inert gas or purging gas is there. So precursor A is deposited here, again precursor B also sit on this layer A, and then we have layer A and B, and we can find out the composition, desired composition for the final films, and again this process will be repeated till we get the enough thickness. Suppose for silicon oxide deposition, we need this substrate here, silicon surface is here, and silicon precursor is used in gas form, and then it is deposited here, and again some purging gas like oxygen is deposited, and now we have SiO2. These are layer by layer deposition. So this process is known as the atomic layer deposition, and it is very useful in case of the semiconductor industry. So there are some certain differences in physical vapor deposition, chemical vapor deposition, and atomic layer deposition. So in the case of PVD, we have seen that atoms as the source material, whereas in CVD molecules are as source materials. And in PVD, most of the time solid source materials are used, and they are heated up, whereas in CVD solid, liquid, gas can be used depending on the situation. PVD system need very high vacuum, whereas in this case the fluid dynamics or the gas dynamics is important. And in PVD most of the time we can deposit elemental film, whereas in this CVD we can deposit the molecular film or compound film. Now all kind of films can be deposited, and in PVD the substrate can be at room temperature, but in CVD case the substrate needs the elevated temperature or high temperature, and alloy films can be deposited by this PVD, and in CVD elemental and compounds are okay, but alloy films are difficult in case of the CVD. Thanks for watching this video, and in this video we have discussed different synthesis techniques for nanomaterials and nanoparticles, and in next video we will discuss the characterization techniques for the nanomaterials. And if you are new to this channel, then please subscribe to this channel. See you soon. Thank you very much.